Sound is everywhere. We hear it all the time. A high note from a singer, a deep rumble of thunder, but it's totally invisible. Have you ever stopped and wondered, what does that sound actually look like? Well, today, we're going to pull back the curtain and find out.
So that's the big question, right? How in the world do you take something you can only hear and turn it into something you can see, something you can, measure? Turns out the answer lies in a pretty cool piece of tech. And here it is. This machine is what makes all the magic happen. It's called a cathode ray oscilloscope, or much easier, a CRO. Its whole job, its entire purpose, is to translate those invisible sound waves into a picture we can see on a screen.
So how does it see sound? It's actually a super straightforward three-step process. First, the sound waves go into a microphone. Pretty simple. Then, that sound energy gets converted into an electrical signal. And finally, the CRO takes that signal and draws it as a wave on its screen. So it's just input, convert, and display.
Okay, before we dive in, let's get our vocabulary straight so we know what we're looking at. These waves have high points and low points. The highest points are called crests, and the lowest points are troughs. Just think of them like the peaks and valleys of a mountain range.
All right, we've got our tool, we know the lingo, we are ready for our first investigation. Cracking the visual code behind pitch.
We all know what pitch is. It's what makes a tiny bell sound high and a big tuba sound low. But that's just what our ears tell us. The CRO is what lets us see what's actually physically different between those sounds.
So, what's the visual giveaway? When we show the CRO a high-pitched sound versus a low-pitched one, what do you think we're going to see? What's the clue?
And whoa, there it is. The difference is crystal clear. On the left, for the high-pitched sound, the wave is really crowded. The peaks and valleys are all bunched up together. But look at the right. The low-pitched sound has waves that are way more stretched out and relaxed. Now, this crowdedness has a proper scientific name. It's called frequency. It's literally just the number of complete waves that squeeze into 1 second. So a high-pitched sound has a high frequency. A low-pitched sound has a low frequency. They're one and the same.
This brings us to our first key takeaway, a super simple rule to help you remember this forever. The more crowded the waves, the higher the pitch. That's it. It's a perfect visual shortcut.
Okay, so pitch is all about how crowded the waves are. We've got that down. So let's move on to our second investigation and decode loudness.
Just like pitch, loudness is something we just get, A whisper is soft, a rock concert is definitely loud. But how do we see that difference? How can we measure it? You got it. We look at the wave.
And here's the secret. For loudness, it's not about how crowded the waves are, it's about how tall they are. This height, measured from that flat center line all the way up to the crest, is called the amplitude. And check this out. It's so obvious when you see them side by side. On the left, the loud sound creates this really tall, dramatic wave. That's a huge amplitude. Now look at the right. The soft sound makes this little short wave with a tiny amplitude. The difference is just massive.
So this gives us our second rule, and it's just as easy to remember as the first one. The taller the waves, the louder the sound. Height equals loudness. Plain and simple.
Okay, we've done all our detective work, we've gathered all the clues. Let's put it all together and review the 2 simple rules of sound that we've uncovered. So here it is, the whole shebang. For pitch, which is just how high or low a note is, what we're looking at is the frequency, or the number of waves. And the simple rule, more waves equals a higher pitch. Then we have loudness, how loud or soft a sound is. That corresponds to amplitude, the height of the waves. The simple rule there, taller waves means a louder sound. That's all there is to it.
And that's really the coolest part about all of this. By using a tool like the CRO, we can take sound, something that's just an invisible experience, and turn it into a visible, measurable wave. We can actually analyze it with total precision. But this leaves us with one last really fascinating question. If a guitar and a flute play the exact same note at the exact same loudness, they should have the same frequency and the same amplitude, right? So why do they still sound so completely different? What other secret is still hiding in the shape of that wave?